Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 9-4 lesson on algebraic limits of piecewise functions. In this one, we will be finding limits of piecewise functions without using a graph, and while we're at it as an extension, we will also find limits of absolute value functions. To start us off, I'm going to begin by defining piecewise functions. So this is just a function that's made of smaller functions, which I like to call rules, and each of these rules has its own domain, or x values where it works. We're going to start with a visual of piecewise functions before we try the purely algebraic end. So here's a picture of a piecewise function. We've got 1, 2, 3 different rules going on here at least. One is a line, one's a parabola, and one's another line. Now you'll notice that there are certain x values where one rule ends and the other begins. I'm going to be referring to these as border values in this lesson. These are x values where one rule ends, the other begins. With this in mind, pause the video and using the graph that I just gave you here, see if you can find f of a and limit as x approaches a for each of the 5 a values, x values, in this table. All right, let's see how that worked out. So for f of -3, that's the function value at -3 here. We just look it up on the graph. It's -2. The limit at -3 from the left and the right, and therefore two-sided, is also going to be -2. Moving on to the border value of x equals -2, our function value there is this solid dot, which is at 0 for the y value. But the left and the right side limits don't match up there, so dne is what we're writing for the limit at that border value. Moving on to the non-border value of 1, the function value is 1, the left and the right and the two-sided limit are also 1, so those match up. Moving on to our next border value of 2, we see that our function value there is 4, and then the left and the right sides, they're coming at different angles, but they end up in the same place. They still end up having a value of 4. And then finally, the non-border value of 3, we have a y value there of 4, so that's f of 3, and the limit at 3 is also going to be 4 as you look at it from the left and the right side. So just kind of looking at this table and see if we could strategize for when we don't have a picture to work with. It appears that at our non-border values, -3, 1, and 3, the function value and the limit were the same. So if you had an algebraic piecewise function to work with and you just plug in a non-border value, you know whatever you get back is also going to be the limit. Now what about these border values? Well, we saw at this border value, the function value and limit were not the same, whereas at this one they were. So just moving ahead, we know that at border values, the function value and limit can be different. So when we're doing border values, we're going to have to use a different strategy. At this point, we're going to take a look at the algebraic end of piecewise limits. Here's a piecewise function that should actually be kind of familiar to you because we just saw the graph of this thing in the warm-up. The way these are set up, on the left side here, you have all the different function rules, and on the right side, you have all the domains where each individual rule actually works. For example, this x squared only works, is only graphed between -2 and 2 for x values. So we're trying to find the limit of this thing at 1, -3, and 3 for this particular example problem. Now why do you think I picked those particular x values? If you take a look at the intervals for my piecewise function, you'll notice that 1, -3, and 3, none of them are border values. They're all squarely inside one interval or another. So to handle non-border values, since we saw that the function value and the limit are exactly the same, for 1 and 2-sided limits, both of them at non-border values, we're just going to plug the x value that we're approaching into the function. So we'll do the first one together. This one, since this is a non-border value, since 1 is not any of these border values, we're really just doing f of 1 here, and we're going to accept whatever result that gives us. Now how do I actually plug 1 into this piecewise function? To do this, we're just going to use the rule whose interval contains the input. So we're inputting 1 for the x value, so we're just going to look up the rule where 1 falls. That would be this middle rule right here. 1 falls between -2 and 2. So we're just going to use this x squared rule when we're evaluating f of 1. So x squared really means 1 squared in this situation, which means that our limit and our function value there is just 1. Pause the video and see if you can do these other two examples. All right, so for this one, this is a non-border value. We're really just doing f of negative 3. Negative 3 is in this first interval. Negative 3 is less than negative 2. So we're just going to be plugging negative 3 into the 2x plus 4 function. So 2 times negative 3 plus 4. That's negative 6 plus 4, which comes out to negative 2. And then finally, this last one, 3, not a border value. So we're just plugging 3 into the piecewise function. 3 happens to fall in this last interval. It's bigger than 2. So whatever you plug into this last interval, you're just going to get back the value 4. For this next example, we're trying to find the limit as x approaches negative 2 for the same piecewise function we just used. Now for this one, you might have noticed that negative 2 is a border value. It's the end of one rule and the beginning of another. If we were just doing f of negative 2, then we would just use this first rule because it says x is less than or equal to negative 2. But we're not finding a function value. We saw in our warm-up that function values and limit values can be different at these border values in piecewise functions. And again, let me just go back and show you the picture. Function value and the limit didn't even exist at that particular time. So we need to be really careful with these border values. We have a special process for two-sided limits at border values. It's really the same process we've always been using, but we're going to do it algebraically. It's just the whole find the left and the right limit and compare them idea. So for our first step, we're going to find the left-sided limit. So I'm going to start by writing left and then limit as x approaches negative 2 from the left of f of x. You don't have to write the word left, but I'm just putting it there to be extra clear. So how do we find a left-sided limit now at a border value? Well, these border values, I like to think of them as splitting up these rules into a before and after rule. You have the rule that happens before you get to negative 2, and you have this rule that's happening after you get to negative 2. For the left-sided limit, you're just plugging negative 2 into the before rule. So that would be this rule right here, this first rule. So in this case, this is just going to be 2 times negative 2 plus 4 using this first rule. That's negative 4 plus 4, which means we have a left-sided limit of 0. Now we also need to know the right-sided limit to see if it matches the left-sided. So for the right-sided limit, and I'll write right, and then limit as x approaches negative 2 from the right side. For the right-sided limit, what do you think we have to do? That's right, we have to plug our value into the after rule. So that would be this rule right here. So we would have negative 2 getting plugged into x squared, which we know comes out to 4. Now as our last step here, once we've got the left and right rule, we just compare them. If the left and right limits match, then the two-sided limit is just whatever they happen to agree on. And if they don't match, just like we did graphically, we would say the two-sided limit does not exist. Do our left and right match here? Well, 0 and 4 are not the same number, so we would then say that the two-sided limit as x approaches negative 2 does not exist. We'll do one more example using this piecewise function. Pause the video and try this one on your own. All right, now hopefully you noticed that 2 is a border value, which means that we have to show the left and the right limits before we make any conclusions. So our left-sided limit, using our before rule here, this is going to be 2 plugged into x squared, which is just going to be 4. And for the right-sided limit, as x approaches 2 from the right side, we're using this after rule here, which always just returns a value of 4 no matter what. Since 4 equals 4, since these match up, we can conclude that our two-sided limit is also 4. For the final example in this lesson, you might be wondering what a problem on absolute value is doing in a lesson on piecewise functions. As it happens, absolute value actually is a piecewise function in disguise. To make numbers positive, we either leave them positive if they already are, or if they're negative, we multiply them by negative 1. Different rules for different numbers. So to find the limit for one of these, we're just going to rewrite this in piecewise function form. So to start this process, I'm just going to let all of this absolute value stuff equal f of x, just so I can write f of x instead of rewriting this every time. And then we're going to have this be a piecewise function. Now, a piecewise function, you need a border value to separate one rule from another. The border value in this case is going to be where the absolute value expression, the stuff inside the absolute value here, has a value of 0. So in this case, that would be x equals 2 as a border value because 2 minus 2 is 0. So we have one rule for the places where x is less than 2. That's going to be the rule where we cover what happens when the stuff inside here has a negative value. And then we have another rule for where x is greater than 2. That'll be the rule where we cover what happens when the stuff inside here is already positive. Next, for the lesser rule where we're trying to turn negative things into positives, we're just going to replace the absolute value with a negative parentheses. Essentially, to simulate the make it positive effect, we're going to take all the stuff inside here and just multiply it by -1. So instead of writing this here, I'm going to write negative parentheses x minus 2 over x minus 2. Now for the other rule, this is a little bit easier because we just want to leave stuff the way it is if it's already positive. For this rule, we're just going to drop the absolute value. So for this one, we'll just write x minus 2 with no absolute value over x minus 2. And at this point, we would try to find the left side limit and the right side limit. But you'll see that if you try to plug in 2, and you might have noticed that there's no x equals 2 case, if you try to plug in 2 here, you're going to end up getting some kind of undefined or indeterminate form. So we can actually go one more step on this problem, and you might notice that this is x minus 2 over itself. Well, that's really just 1 if you cancel those out. And this up here is really just -1. So I'm just going to rewrite this to be -1 and +1 instead of what we originally started with. With this in mind now, go ahead and see if you can finish this problem on your own. All right, so if we're trying to find the limit as x approaches 2, we need our left side limit, the limit as x approaches 2 from the left side. That's just this first rule right here. If you plug 2 into this rule, quote unquote, you're really just returning -1 no matter what. So that is our left side limit. For the right side limit, we're using this rule, which automatically returns 1. So since these do not match up, we would say that there is no limit, two-sided limit, as x approaches 2 for this problem. So with that, we are absolutely done with piecewise limits, for now at least. Till next time, Mr. Sutton signing off.